In this video, we are going to discuss work and kinetic energy and the link between the two. So, in physics, work has a very specific definition, and that is force dot product with displacement. So the dot product of the force applied to some object dotted with the displacement of that object. We know from our knowledge of dot products that the dot product of two vectors is a scalar. So work, my symbol W here, does not have a vector symbol above it because it is just a scalar quantity. It's just a number. Just to make sure that we understand it, work, the units of work must be newtons multiplied by meters is Newton meters, which we call a joule. So the symbol J stands for newtons times meters, that is force times distance. Okay, to see why we might care about this, let's think about just pushing a box along some surface with some force. So I have some force that is pushing down on my box as it glides across a surface with no friction. Now, what I might be interested in is, say I do this, I push this box for some distance, and I want to know how fast the box is going after that distance. So let's say that I push the box over some displacement d vector here, right? You could also write this as a delta x vector, the displacement vector. But traditionally for work, it's written as the d vector. So my box moves some distance to the right here, and I call that d vector. Well, we know from how the dot product works that what the dot product does is it takes the component of one of the vectors. So in this case, we'll take the component of the force vector that is in the direction of the displacement vector. That is the F parallel vector. So what we could do is we could write, say for example, my force vector as the x component of the force vector in the I hat direction plus the y hat component of the force vector in the j hat direction. My displacement vector would be just the displacement vector in the I hat direction, or the magnitude of the displacement vector in the I hat direction. And so F dot D is I hat times I hat is the x component of the displacement vector plus 0, right? So this tells us the multiplication of the force in the direction of my displacement, which I can just write as Fx here, multiplied by that displacement vector. And the dot product is really handy here because if we want to think about how this box accelerates, this y component of my force does not help the box accelerate, right? The y component is pushing down into the ground. It's going to be counteracted by my normal force, and the box moves only in this direction. So if we went back to, say, our forces picture of this situation, you would say that the acceleration of my box depends only on the x component of my force here, and you would solve for that x component in terms of your Newton's second law. So the dot product basically does exactly the same thing. It says, well, which component of my force is actually helping me move? Oh, it's the component of my force in the direction of my displacement. I will just find that. The cosine method also works because if I think about my displacement vector here, my force vector here, this component, right? So this distance here is fx equals f cosine of theta. So fx times d really equals f d cosine theta. And just a quick note, the reason why I don't have magnitudes here, why I allow these components to be both positive or negative, and I have magnitudes here, is because in this case, the cosine of theta tells me if the two vectors point in the same direction or not, right? So remember, if the cosine of theta, if theta is less than 90 degrees, my cosine of theta is positive, and my two forces point in the same direction, and I should have a positive dot product. And if theta is less than 90 degrees, I should have is greater than 90 degrees, the two forces point in opposite directions, or their parallel components point in opposite directions, and I should have a negative dot product. In this expression here, I am allowing fx to take on positive or negative values, as I am with d. So if fx has a positive value and d has a positive value, then they point in the same direction, and I should get a positive dot product, right? If fx points in the negative direction, which is not the case here, but it could, right? I could imagine drawing a force that points in the negative direction, then I'll get a negative dot product if I have an x component of my force pointing to the left, while my displacement vector points to the right. So here I need to keep track of the sign of these components to figure out if my dot product is positive or negative. Whereas here, the cosine takes care of it for me, and I just write the magnitudes of my force and displacement vector. Now let's do a specific example of a force with a displacement. So again, we have a box sliding across a frictionless surface. No friction. And here we have a 4 Newton force applied at a 45-degree angle. So I can write the work done by this force as force dotted with displacement, which looks like fx times d, right? The x component of my force, because my d vector points only in the x direction, I use the f component here, which in this case is negative, and I disregard this y component, right? That's what the dot product does. So here I have negative 4 newtons multiplied by the cosine of 45 degrees. So 45 degrees is this angle here, and I have a negative sign inserted because I am using a standard plus x plus y coordinate system. So pointing to the left is negative. And I multiply this by 3 meters. Notice that my dot product is going to come out to be negative. It's going to come to be negative 12 cosine of 45 degrees, and that all has units of joules. The dot product is negative because the force is acting in the opposite direction of the displacement. Now let's think about how we can talk about the change in motion of this box and relate that change in motion to work. So let's think about the same situation, a box on a frictionless surface that is being pushed with some force. And we're going to think about it in the context of this equation. So we want to know, how does the box's velocity change as it accelerates? And we have some acceleration in the x direction over some displacement, right? So our delta x is the same thing as the magnitude of our displacement here. Okay, so what I'm going to do with this equation is I'm going to multiply both sides by the mass. So my box has some mass, and I'm multiplying both sides of the equation by that mass. Now, the thing I want to focus on first is this here, because this looks like the force in the x direction, right? And this looks like my displacement. So this whole thing looks like the dot product of force with displacement, right? I take the x component of my force, that is the component of my force that is in the direction that I'm moving, and I multiply it by how far I moved in that direction. So this whole thing looks like work, well, with a 2 in front. So the last term here is 2 multiplied by the amount of work that my force has done. By force F. Note that only the x component of my force actually influences the acceleration of my box, right? The y component of my force just pushes the box into the ground more and helps increase the normal force, but doesn't actually help increase the velocity of the box in the x direction. Only the x component does that. Okay, so now I'm going to rewrite this equation as 2 times the work equals m Vx final squared minus Vx initial squared. Or work equals 1/2 times the mass of V final squared in the x direction minus 1/2 m Vx initial squared. Okay. And this quantity here, the quantity 1/2 mv squared, in general, this quantity is called the kinetic energy. That is, how much energy of motion does the object have? So the kinetic energy is called the energy of motion, and the equation 1/2 mv squared gives you its value. So this looks like the final kinetic energy minus the initial kinetic energy. So we can write that the work done equals the change in the kinetic energy of a system. So the work done on a system is equal to how much the kinetic energy, this 1/2 mv squared quantity, changes over time. So if I know V initial and I know the work, I know V final, right? And the reason that this is really nice is everything in this equation is a scalar quantity. I don't have to worry about components. I don't have to worry about direction. I know that if I did this much work, I changed the velocity of my object by this much, right? And really this is because when I calculated the work, I got rid of all of the forces in the not direction of motion, right? I got rid of my y force, and I only concentrated on my forces in the direction of motion. And this is what the dot product of F dot D does for us. It eliminates any forces that aren't directly contributing to accelerating the object and gets us to this change in the kinetic energy, the energy of motion of the object. Now let's just look at a simple example of how we can use this relationship between work and change in kinetic energy. So the problem that we're going to do is a box is initially moving at 4 meters per second to the right. It's moving along a frictionless surface here, and the box has a mass of 3 kilograms. If a 10 Newton force acts down and to the left at an angle of 60 degrees below the horizontal, we want to find the kinetic energy at the very beginning, and we want to find the kinetic energy after the box has moved for 2 meters to the right. Okay? So, the first thing that we want to do is we just want to calculate the initial kinetic energy. That's easy. So it's just that the initial kinetic energy is 1/2 mv initial squared, which looks like 1/2 times 3 kilograms times 4 meters per second squared. 4 meters per second, and the square goes on the outside. And that looks like 8 times 3 is 24 joules. So the initial kinetic energy of my object is 24 joules. If I want to find the final kinetic energy, I can use the fact that work equals KE final minus KE initial, or that is kinetic energy final equals kinetic energy initial plus work. Okay, so now if we can find the work, we know the kinetic energy initial and we can find the kinetic energy final. Okay, so if I want to find the work, I simply have to do F dot D, the force multiplied by the displacement. I know from my problem statement that my displacement is 2 meters to the right. So my displacement vector looks like 2 meters to the right. And my force vector points down and to the left. So my x component of my force, I'll erase this here. The x component of my force is going to be negative the magnitude of my force, which is 10 newtons, right here. So it's going to be negative 10 newtons multiplied by the cosine of 60 degrees, which is negative 5 newtons. Okay, so my work is going to be equal to the x component, right? So this is my x component of my force, the part of my force that points in the direction of my displacement. So it's negative 5 newtons multiplied by 2 meters is negative 10 joules. So I know my work, negative 10 joules. Notice that I expect this work to be negative because my force points in the opposite direction of my displacement, right? So my kinetic energy final must be 24 joules minus 10 joules is 14 joules as my final kinetic energy. From this, I could of course find my final velocity as well, because I can relate my final kinetic energy 1/2 mv final squared. Since I know my mass, I know my final velocity as well.